of basically this concept of signal aliasing and how we're going to choose our sampling frequency in order to avoid basically aliasing our signal, we can now get to the work of performing and rewriting our expressions, and specifically our expressions for our harmonic coefficients, which we previously developed for continuous Fourier transforms, and now do that for discrete Fourier transforms. So we need to basically convert these integrals that we all know how to program into Mathematica and solve by hand. For some of you integral lovers, we have to convert this now into summations, because now we don't know what this algebraic expression is. So we are working with a discrete data set. So we still have a function y of t, but we don't know the full functional form. We have basically data points here. So data points that are given as a function of time, and the interval between these data points is some interval delta t. So I'm going to have some data point at y, or some y value. So this is my y sub 1. I'm going to have some value y sub 1 at a point here, r1 delta t. So that value could be, for example, let's say this is 5, and the next one is 10. So y sub 1 is going to have some value 5. At my second delta t, so this is my first delta t here, at my second delta t, y2, it's going to be 2 delta t. And that's just going to be equal to the 10 here. Again, it doesn't have to be this multiple, this could be 8. Let's do that. 8, for example. And et cetera, et cetera, et cetera. And I'm going to have some y r value at some r delta t. And it's going to be some value, who knows. But basically, we are now working, instead of an algebraic expression, we're working with a discrete data set that's going to vary as a function from r goes from basically a value of 1 in integer values to n, the total number of my data points. Because at the end of the day, my period is going to be t is equal to n cell last time, or t is equal to n for sub s. Anyways, more on that a little bit later. So we no longer have this continuous function, discrete data, or discrete function, where r is going to vary from 1 to n, so we can start to rewrite our expression. So let's go ahead and look what we can plug in. So we know here that t, excuse me, my other computer is loud. I'm going to mute that just in a second right here, so no more distractions. N times delta t. So I could plug in for that right here. So that takes care of that. We know that we're going to rewrite this, my y of t, with this function right here, or y as a function of r of delta t. So instead of taking the integral, we're going to actually plug in these y values at different, essentially r, or r times, again, these integer values of delta t. So again, these are integer, r integer. It's an integer counter for discrete data points. So and instead, for dt, we're just going to replace this with this r delta t, because again, that's what we're working with, discrete data sets. And the summation, we're going to sum, as we can see here, not from r to infinity, but from r to n. So let's go to here. Actually, that's a typo right there. So we are not going to go from, unless we have an infinite number of data sets, that would be nice, from r from 1 to n, as seen below. So let's go ahead and basically, it'll look a little bit like this. So let's just plug in 2 over n to t, summation from r equals 1 to n, pi of r delta t times cosine of 2 pi n times, again, delta t over n delta t times delta t. So that's messy. That's why we have LaTeX. So we're just replacing again. We don't have discrete. Again, any t is going to go to delta. Because again, we don't have discrete, time data, or we don't have this continuous data set. We have discrete data sets now. So let's see what we could pull out here. So this is going to cancel here. My r is going to remain. This I could pull out over here, and that's going to cancel here and here. So now what I'm left with is this function right here. So 2 pi r, again, these are my y values. And this equation may seem confusing. It probably does. Hopefully it does a little bit when we're just working with it right now symbolically. But we really need to understand how we could use this function. What are we plugging in order to kind of calculate our frequency spectrum and perform a correct discrete Fourier transform analysis. So our harmonic coefficients are going to be like this. And we know what a sub 0 and b sub 0 is going to be. So we'll get to that in just a bit too. So we know that sine of 0 there. We'll come to that in just a little bit. Now, but I want to stop right here and let's look at the limits here. Why are we stopping at this n why are we stopping at harmonic coefficients n from 0 to n over 2? So why do those harmonic coefficients stop there? Why don't we go to n? Well, it has to do with a special frequency, a really, really important frequency that's called the Nyquist frequency. So the Nyquist frequency is simply half of our sampling frequency. This Nyquist frequency is the maximum frequency that we can resolve in a frequency spectrum graph. So once we choose our f sub s, so if my f sub s is 100, I can only accurately sample or accurately resolve frequencies in my frequency spectrum that are basically my frequency spectrum is going to go from, let's say my delta f, my period is 1 hertz. So my frequency spectrum is going to go to basically 50 hertz. That's the only, once you choose that sampling frequency, our frequency spectrum graph is going to go to half of the f sub s. So f sub s over 2, from 0 to there. So we're going to prove in a second, but the reason is because these are the only frequencies lower than our Nyquist frequency. Well, frequencies at our Nyquist frequency and below, they are going to be accurately sampled. So we're not going to have kind of this signal aliasing and these other issues. But frequencies above the Nyquist frequency will basically appear as mirror images of our lower frequencies in our frequency spectrum graph. We're going to prove that and actually show that quantitatively once we do our first example for discrete Fourier transforms. But just trust me for now, but that is going to be how our frequency spectrum graph is going to look like. And we'll show that in just a second. So let's go ahead and we have a couple of really key definitions that we're going to kind of come across. So we know that our delta f is 1 over t. That is our period. So in the discrete Fourier transform world, we know that that is also equal to n delta t. We also know that that is equal to f sub s over n because of our previous definition. Sub s equals 1 over delta t. You could start to see how these definitions are starting to pile up. So you want to have these organized and see what you want to work with. And we can also rewrite our delta f in terms of 2 times, we know that our Nyquist frequency is just f sub s over 2. So my f of my Nyquist, so that is equal to f Nyquist divided by n. So our frequency spectrum graph, additionally, we always plot this in terms of delta f. So our maximum frequency, our f Nyquist, is going to be what? We could rewrite our f Nyquist as equal to n over 2 times delta f. So again, that's exactly the limits that we just kind of put. We know we're going to do harmonic coefficients n times delta f. So it's n, our maximum frequency in our Fourier spectrum is going to be our Nyquist frequency, which is just n over 2 times delta f. So same thing as we've been dealing with previously. So once you pick a sampling frequency, which is usually given in a chart, you could solve, again, for the maximum frequency instantaneously. It's the same as our Nyquist frequency. So that was fairly quick, but hopefully, again, these will kind of, these concepts will become more clear once we actually solve and do a problem. So more examples are coming, but again, the key thing here, we're going to move from our, basically, this integration formulation or formalism to our summation idea here. So summation, because again, we're working with a discrete data set here. And then we're going to go from the summation into, or we're going to use the summation to calculate harmonic coefficients. But again, the limits of integration change depending on this Nyquist frequency here. And again, all this will hopefully come together when we work with some examples and do several example problems, and then obviously in your problem set as well. So next time we are going to work with an example, and here's our signal that we're going to produce on our oscilloscope, and next time we're going to get into this. So we are going to look at this next time, solve a discrete Fourier transform, and I'll see you all in the next video. Exciting, first discrete Fourier transform. I'll see you in a bit. Thanks, bye.